Let's come back to the first situation. Let's recall. In situation A, the genes are found in the autosomes and there are only a pair of alleles. One is dominant over the other that control the trait, okay, or the characteristic of that organism. And the example will be a rhesus factor. Now, what is rhesus factor? We always hear of the blood type, okay, blood type A positive or A negative. So the positive and the negative refers to that rhesus factor. If you are A positive, that means to say that you have the antigen A on your red blood cells, on the surface of your red blood cells, as well as the rhesus factor on the surface of your red blood cells. If you are A negative, that means to say that you only have the antigen A, but not the rhesus factor on the surface of your red blood cells. The shape of the earlobe, hair color, and then the disease like thalassaemia, albinism, sickle cell anemia, all these follow the Mendel's law. So in other words, it is exactly the schematic diagram is exactly the same as what we have done in Mendel monohybrid and dihybrid inheritance. Okay, so let's start with let's say rhesus factor. Now, first of all, we must be given scenario first. So given that there are two types of alleles, one is Rh positive, the other one is Rh negative, and Rh positive is dominant over Rh negative. Okay, so let's see. Okay, let's say the father he has positive blood, however he is a carrier, and then the mother is negative. Let's see. So what is a possible genotype for the mother? The mother must have both Rh negative allele to be negative, because as shown here, the Rh negative is the recessive allele. Then what about the father? The father is a positive and a carrier at the same time, so it carries both alleles. So during the formation of gametes, the father is going to produce two types of gamete. One is Rh positive, the other one is Rh negative. The mother can only produce one type of gamete, which is Rh negative. Remember to label this process. It is going to give you marks also as meiosis. Then during random fertilization, complete the whole terms. Rh positive can combine with Rh negative, giving rise to this genotype. This one can also combine with this to give you Rh negative, Thus, the phenotype of F1 generation would be positive, carrier, and then negative. So that means to say that regardless of the gender of the phenotype, because this is not a sex-linked disease, 50% will get will be the negative. Will be having the negative blood. Now the other 50% they have positive blood. However, they are carrier. Now let's look. What about the inheritance of thalassaemia? What is thalassaemia? I have to refer to book. Now, thalassaemia is a condition in which the body is unable to synthesize the protein needed for the synthesis of red blood cells. So that's why the thalassemic patient suffer from serious anemia because of the inability to produce the healthy red blood cells. And luckily, this is a recessive disease. It means to say that you need to have both recessive allele to get this disease. Okay, let the dominant allele be big T and the recessive allele be small t. Now, since this is not a sex-linked disease, so I don't have to state whether the genotype of the parents is X or XY. So we start with the schematic diagram again. This is the symbol for male. A male is crossed with a female. Both are parents. And normally in the questions, we must be given information about the phenotype of the parents first. Let's say the father is normal. Is normal. However, he is a carrier. The mother, let's say, is also normal and carrier. And from the appearance, they are just like normal human being. Okay, since they are normal from the appearance, they do not know they are actually the carrier of thalassaemia. However, the phenotype of thalassaemia will be shown in the offspring. Let me show you. So first, let's write down the genotype of the father first. The father is a carrier, so he must be heterozygous. He is normal because he has this dominant allele. The mother has also big T and small t. During formation of gamete, this pair of allele must separate. Alright, so normally we prefer to put a circle, okay, around the gamete to show that they are gametes. But it is perfectly okay if you don't circle it. During the process of random fertilization, big T can combine with big T to give F1 generation this genotype. Big T and big T, big T and small t, big T and small t, small t and small t. This must be normal. This is also normal. However, he or she is carrier. This F1 generation is again normal. However, he or she a carrier. And then the small t is thalassaemia. That means to say that this offspring has thalassaemia. And the ratio, if you look at them, you have 3 normal. You have 3 normal to 1 thalassaemia. So what does it suggest here? It is always advisable to do the blood test to determine whether you are the carrier of thalassaemia before you get married. Because from the appearance, we might appear normal, but who knows that we are actually the carrier of that mutated or recessive alleles, and it might lead to our children having thalassaemia, even though the percentage is not high, it's 25%. However, if the kid has thalassaemia, it will be a nightmare, for this patient, because he has to visit the hospital frequently to get the blood transfusion to replace the dead or and the malfunction liver cells. So do the blood test before getting married.